Hello. In this video I'm going to address how we can progress from similar triangles to trigonometric ratios. So I'm going to begin with a classic example of the use of similar triangles. So let's say, for example, you have a tree, right? And you don't know its height. But you want to know its height and you have no way of really like climbing it or measuring it, that sort of thing. But you do know that here's the sun, right? And it casts, the sun's rays cast a shadow, right? So now I have a vertical and a horizontal line where they come together. There's a right angle, 90 degrees, and always across from 90 degrees is the hypotenuse, right? And this shadow, let's say we were to measure this shadow, which we can because it's on the ground, and let's say it's 69.28 feet. Okay? So then, if I want to try to figure out the height of the tree, I can use similar triangles and say, well, all right, the tree's too tall for me to measure, but let's say I take a board that I know is 10 feet tall. And then of course the sun's rays at that location and that time of day are going to affect it the same way. So it'll cast a shadow. And of course I can measure this on the ground, 17 point, let's say 32 feet. And although I don't know this angle, I know that the angles are the same, right? And this too is a right angle. So since the angles here are the same because the sun's rays are parallel and affecting everything in that region the same way, with the same angle, then I have two of the three angles are the same. Obviously the third angle must be the same also, right? 180 degrees minus this minus that will give me this angle. And so they're similar triangles. Because they're similar triangles, I can set up a proportion and say something like, what I'm looking for, H, is to 69.28 as 10 is to 17.32, right? And then if I want to solve this, I can just multiply both sides by 69.28. Right? And so these cancel out, and I'm left with H equals 10 times 69.28 divided by 17.32, and you'll get 40 feet. Okay, so that's sort of a classic example. All right, but let's suppose you look at this and say, well, you know, I wish I could generalize this more. You know, how can we use or increase the power of similar triangles? Right? So you say, well, all right, maybe we can make this a little bit more abstract. What we did essentially is we had a small triangle and a large triangle, both of them similar, right? Both of them similar. And if we were to be a little bit more abstract, we could say, here's the lengths of these sides, side A, B, C, and then let's say big A, big B, big C. And what we did is we said, okay, big B is to A as little b is to A. That's what we did. And that theoretically works. But remember, somebody could have set it up as, well, let's see, instead of this way, I could have said big A is to big B as little a is to little b. And then, of course, they could have written it the other way around, right, and said, well, little b is to A as big B is to big A. And again, you could have done this, right? And that's just staying within one triangle, so I could have instead crossed triangles and said, well, little a is to big A as little b is to big B, and you know, keep going. Of course, you could do the same thing, get all these different variations. You could say big A is to little a as big B is to little b. You could have written them the other way, B here. All right, so there's so many variations though, right? So although this is getting a little bit more abstract, perhaps a little bit more powerful, going from the concrete to the abstract, there's still an awful lot of room for like so many ways of setting it up. So perhaps is there some way we can standardize this a little bit better? So you say, well, okay, if we think about it, what was happening is the sun's rays were casting a shadow and basically creating the same angle, right, on both objects, the board and the tree. So essentially what's happening is we had an angle, theta, and when you think about it, theta here can create, if you drop a perpendicular, you can create an infinite number of similar triangles. I mean, it would just go to no, there'd be no end, right? There should be perpendicular here. So really what we want to do is take a look at, maybe we can relate this to an angle, right? A specific angle. So if we're going to do that, then let's standardize that a little bit more and say, okay, if we have a right triangle, right? And basically, really, when we talk about similar triangles, we're talking about similar angles. So the angle is what's really the driving force here. So relative to this angle, what can we do? We can standardize the names of the sides a little bit more and say, okay, well, across from the right angle is always the hypotenuse, which we can abbreviate HYP. Across from the angle is the opposite side, or OPP. And of course here, adjacent to the angle, abbreviated ADJ. Now this is a little easier because what happens here then is this angle, which is basically creating all these different infinite number of similar triangles, I now can say that, well, how many ratios could I possibly come up with? Because that's what we're really doing here, is just forming ratios. How many ratios could we possibly form? Well, we could have adjacent to opposite, or we could have adjacent to hypotenuse, or we could have opposite to hypotenuse, or we could have opposite to adjacent, or we could have hypotenuse to adjacent, or hypotenuse to opposite. There's really only 6 possible ratios that you can have, right? So since there's only 6 possible ratios, that's much easier to work with. You don't have all these tons of variations, right? And we haven't even included C on these right here. All the ratios that could come from that. So we gave them specific names. Okay, so adjacent, over opposite is cotangent. Adjacent over hypotenuse is cosine. Opposite over hypotenuse is sine. Opposite over adjacent is tangent. Hypotenuse over adjacent is secant. And hypotenuse over opposite is cosecant. Okay. Now, something that's extremely important here is all of these ratios are a function of the angle. Because remember, we're talking about similar triangles. They're similar because of the same angles. So here, the input. Now these are your 6 trigonometric ratios, which also you can talk about them as functions. We'll see why later. The input to a trig function is always an angle, right? Because you're trying to find out the ratio relative that's formed from the right triangle because of that angle. So how we write this, though, is cotangent of theta. Then you have to have that input. We have cosine of theta, sine of theta, tangent of theta, secant of theta, and cosecant of theta. Okay, so those are the 6 different trigonometric ratios. All right. Now, let me just mention here, obviously some of them are reciprocals of others. So let me just kind of mention here that sine and cosecant, opposite over hypotenuse, hypotenuse over opposite, these are reciprocals. Cosine and secant are reciprocals. Tangent and cotangent are reciprocals, right? So these are the 6 trigonometric ratios. And one of the ways of remembering this, it's sort of a famous, it's not the only mnemonic device, but so, ka, toa. So this is sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay, so that's one way of remembering, and obviously you'll have to remember what are the reciprocals, but they're just the names, because then you know which names associated with which reciprocal, and you remember all the ratios. So this is a way of standardizing things a lot more. Now, what you can do then is say that since this is all based on a specific angle, and then you can find all the ratios for that angle. So how would we do that? Well, here's one way you could do that. So I've got some quadrille paper, and I've done this. I've just marked a 30, a 45, and a 60 degree angle. And what I did is I took a protractor, right, drew a horizontal line, and then at the 30-degree mark, I made a mark on either side, and then drew a line. Same thing for the 45 and 60. Now, this isn't, you know, there's only a certain amount of accuracy that I can get. So, not super accurate, but accurate enough to see what's going on so you can understand the principles behind this. Now, what I'm going to do is I'm going to focus in on the 30 degree. And I'm going to show you what you can do here. So let's say I want to start to build some ratios for the 30 degree angle. Right? And when I say ratios, I mean, let's see where that page is. I mean these ratios, sine, cosine, tangent, that kind of thing. So what I want to do is, in this case I'm using quadrille squares, and I want to drop a perpendicular. Now I could drop a perpendicular anywhere theoretically, but like if I dropped one here, and remember I'm using these quadrille squares to count, to use as a unit of measure for the length here of this side, I would have 1 square, 2 square, 3 squares, 4, 5 squares, 6 squares, and then a little bit. And that's a little too hard to guesstimate. Like, well, how much of a square do I have? So I'm going to look for places where there's you have a full square at the end. So here's one. Okay, here's one. So now how many squares do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 squares on that side for this triangle. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It looks like 16 squares. All right. So let's take a look at that and look at what we have right there. So right now what we just created then using this is the 30 degree angle with 9 squares and then 16 squares. Sorry about that. And then what I'm going to do is find here the hypotenuse is the square root of 16 squared plus 9 squared, right? So now let's go ahead and figure this out. And by the way, of course, this is the Pythagorean theorem, a squared plus b squared equals c squared, where I have 9 squared plus 16 squared equals c squared. I'm just basically taking the square root of both sides to find c. So let's take that. Square root of 16 squared plus 9 squared. And I got 18.358, let's say. All right. Now, using our definitions, then, what I would get, for example, here, is that sine of 30 is opposite over hypotenuse. So opposite over hypotenuse, sorry, would be 9 over 18.358. Cosine of 30 degrees would be adjacent over hypotenuse. So 16 over 18 0.358. Tangent of 30 degrees would be opposite over adjacent. So 9 over 16. Let's start getting some numbers here. 9 divided by the 18.35. See, 9 divided by 18.358. So that's 0.4902. Here, 16 divided by 18.358. 0.8716. And here, 9 divided by 16. 0.5625. Okay. So accuracy is not incredible here, but at least it's somewhat close. So, and of course you could do cotangent, secant, and cosecant just by doing a reciprocal of these, so that's all right. So now, that's one triangle we got. Let's see if it stays kind of constant. So now let's see if we find another perpendicular. Because in theory, remember, all of these should be similar, and therefore the next triangle that I make by dropping a perpendicular should also have the same ratios, right? So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And let's see, we were at 16 here. 17, 18, 19, 20, 21, 22, 23. It looks like 23. And now let's do the square root of 13 squared plus 23 squared. And I get 26 point, so on this one I get, I may have to change, here's the, here's what I'd gotten, by the way. I want to make sure you could see what I'd gotten, because I had to zoom in. So when we did the smaller triangle, those are my calculations. Okay. Now I'm going to do the slightly larger triangle, which was 13, 23, and then here 26.420, let's say. So again, here then sine of 30 would be opposite over hypotenuse, which is 13 over 26.420. Cosine would be adjacent over hypotenuse, which is 23 over 26.420, and tangent is opposite over adjacent, or 13 over 23. And let's go ahead and figure out those ratios. 13 divided by 26.420, and here I got 0.4921. 23 divided by 26.420, I got 0.8706, and 13 divided by 23, 0.5652. So there are some discrepancies, but that's because we're dealing with quadrille paper, right? And it's not super precise. So the only thing that is really missing from this is precision. Otherwise, this principle would work, right? And for those of you who are wondering, well, wait a second, this is really weird, you're using little squares. I could have used inches or centimeters or whatever, I could have gotten a ruler out and done this. It wouldn't have mattered. It would have been the same. Because what's really happening is if I call these quadrille squares, QS, and this is quadrille squares, guess what happens? They cancel out. So if I had measured it in inches, the inches would have canceled out, the centimeters would have canceled out, but the ratio would have remained the same. So that's what's really fascinating here. This is what's so powerful, okay? So essentially, if I did this for every angle measure and then charted it, this is what I would get, the old trig tables. So here's an example of an old trig table, right? What they used to have in the past. So you would have, for a particular angle, you'd have the ratio of the sines, cosines, tangent, and then of course you'd know the reciprocals. Now, let's go back then, and let's go back to our original problem where we had, let me see if I can find it, the tree, right, with the sun, and say, well, now that we've developed this more abstract way of doing things, right? Now remember, we started out with similar triangles like this, right? And then we said, well, yeah, and then you can abstract to similar triangles sort of abstractly, but that's just a lot of ratios. And, you know, besides, this would work in this case at a particular time and location on Earth. But now if we go a little bit more abstract and we say, okay, wait a second, we know that similar triangles really depend on angles being the same. Let's make the triangles reference to an angle, so let's standardize things. So here's my angle, here's my triangle, let's name things. That reduces the number of ratios I can get. There's only 6 possible ratios. These are the trig ratios. And then let's go ahead and see if we could actually create something of a chart. Well, yes, you could. If you just had enough accuracy, you could just even do it by hand like this. In your calculator, they use Taylor series, though. But eventually, you would end up with a chart here, right, like this. So now, let's suppose in our example here, with the similar triangles, suppose we had known this was a 30-degree triangle, right? So what does that mean? That means, let's suppose I had the same problem. I have a tree, right? I know that the shadow that it casts, right, that the sun casts on the tree is 69.28 feet, and I cite the tree to be at 30 degrees, right? So I cite the top of the tree to be 30 degrees with an instrument, and now I say to myself, well, wait a second, I did all that abstract thinking, and what I know is all right triangles that have a 30 that we're referencing to 30 degrees are going to follow these ratios. So I'm going to have these ratios available to me. Well, in my case, relative to this angle, this is what I want to know. This is what I know. And relative to this angle, this is called the opposite, and this is called the adjacent. So which two trig ratios deal with that? Deal with an opposite and adjacent? Either tangent or cotangent. So you could use either one. Right? Those are the sides that are being used right now. I don't really need the hypotenuse. So then I say to myself, okay, I'm going to use tangent. So essentially what I'm going to do is say, all right, the tangent of 30 degrees must be equal to the opposite over adjacent, right? That's how we tabulated these. That's how we stored the information, right, by their names and by their ratios. So then I just look up in this chart or in your calculator. Here's tangent. Here's 30 degrees, 0.5774. 0.5774, which, by the way, we were a little off. We had gotten 0.5625 and 0.5652. We could have increased our accuracy. If we had, we would eventually get 0.5774. Also, if you put it in your calculator, I'll just show you that. Let me put all this out. You need to make sure your mode, so check your mode. Come down here, make sure you're in degree mode. We are. Now all I have to do is go tangent of 30 degrees. Press enter, 0.5774, right? 35 would round to 4. All right, so now I know this. The opposite is what I want to know. The adjacent is 69.28. Now to solve this, just multiply by 69.28, right? And now H is 69.28 times 0.5774, and you will get 40 feet, which is what we started with the similar triangles. So that's how we go from similar triangles to trigonometric ratios. Thanks so much for listening.